Alrighty, it is 2, so we're going to go ahead and get started on our last lecture for the course. So today we're going to be talking about power factor correction. And this is kind of a subtopic related to complex power that we talked about on Wednesday. So I'm going to draw a picture of a power triangle or an inductive load. Okay. So let's say that we've got something going on like this. Here is our imaginary axis, and over here is our real axis. And for an inductive load, we know that it's going to be in the first quadrant because their resistance is real and the reactance is real. So our complex power should have a positive phase angle between 0 and 90 degrees. Again, we talked about all that kind of good stuff on Wednesday. So we might have something akin to this. I'm going to call this complex power S old. And it represents what our complex power for our load is doing prior to power factor correction. And the projection of S old onto the real axis is going to be P old, our average power prior to power factor correction. And the projection onto the imaginary axis is going to be Q old, our reactive power prior to power factor correction. And lastly, we're going to have some angle here, theta old, which represents our power factor angle prior to power factor correction. So my question to you guys, and I hope this is a fairly simple one, is if I want to improve the power factor at which this load operates, meaning that I want it to be closer to a power factor of 1, do I need to make that angle theta old larger or smaller?
Smaller.
Smaller, because the power factor is simply the cosine of the power factor angle, and cosine of 0 is equal to 1. So if we want to get our power factor closer to 1, we want to make that angle closer to 0. Okay. So there are two ways that this can be approached. One way is mathematically correct, but it is completely and utterly asinine. So we are going to talk about it very briefly, but I want to be clear, it is not actually done this way. And then we'll talk about how it's done for real. Okay. Before we get into that, though, I want to revisit some quick relationships from our last class meeting. Okay. So in the alternative relationships, what we found was that the complex power in general could be written as the magnitude of our voltage drop across our element or network of interest squared divided by the conjugate of our impedance, or it could be written as the magnitude of our current squared times just our impedance with no conjugate or anything like that. So what I want us to do is I want us to look at what individual elements do to our complex power if we're looking at a system. So for a resistor, we would simply have the magnitude of the voltage squared divided by the resistance, because resistance has a purely real impedance. So the complex conjugate of R plus J0 is just R minus J0, which is literally just R. And pretty similarly, we could see that Uh, in terms of our current, we would just have the magnitude of I squared times R. So that means that resistors, because their complex power is always purely real, all they do is absorb average power in our system. Okay. If we were to look at an inductor, we would have the magnitude of the voltage squared divided by negative j omega L, because that is the conjugate of our impedance. And you might recall that 1 over j is the same thing as negative j. So 1 over negative j is the same thing as positive j in our numerator. So we could write this as positive j times the magnitude of the voltage squared over omega L. And then in terms of current, this would just look like j omega L times the magnitude of our current squared. So we can see that the complex power absorbed by an inductor is always purely imaginary. So there's only reactive power, and it's always positive. So inductors' job from a complex power perspective is to absorb reactive power. Okay. Lastly, we could look at a capacitor. So for our voltage relationship, that's going to look like the magnitude of the voltage squared divided by 1 over negative j omega c. And so I can just pull that negative j omega c up into the numerator, right? Because I'm dividing by the reciprocal is the same thing as just multiplying by whatever's in the denominator of the denominator. So that's going to look like negative j omega c times the magnitude of our voltage squared. Or this could be written as the magnitude of the current squared over j omega c. And another way to express that would be negative j times the magnitude of the current squared over omega c. So from this relationship, where we can see, that capacitor's complex power is always imaginary and always negative, we could say that capacitors supply reactive power. Okay. So the reason why I'm bringing this up is because we can use these relationships and what's going on to figure out how to improve our power factor. Okay. So the first way that I want to discuss, and again, this is really dumb, but it's mathematically correct, would be to add resistance to our system. Okay. So if we increase the amount of average power that is being drawn by our load while keeping our reactive power constant, our power triangle would instead look like something like this. Right? So here is S nu done in a dumb way. Okay. Q is the same as it was. We would have some new average power over here, and we could see that this angle, theta nu, is indeed smaller, so our power factor would be improved. So now let me explain to you why this is so damn dumb, okay? I mentioned it to you on Wednesday, but average power is the power that we as consumers pay for, okay? So essentially, if you try to improve the power factor at which your load operates by increasing the average power drawn, you would be running up your utility bill in order to avoid paying a fine. So you're paying money either way. That's why it works in practice, but it's a terrible idea or say, excuse me, it works in theory, but it's a terrible idea in practice. The whole point of power factor correction is to avoid paying a fine because your power factor is too low. Okay. So if adding resistance isn't the right way to do it, then what is? Okay. Well, if we add more absorbed reactive power, that's going to make Q larger, which means that we're going to be actually operating at a worse power factor. So instead, we need to figure out some way to make Q smaller. And the way that we're going to make Q smaller is by adding capacitance to our system, right? Because a capacitor supplies reactive power or absorbs negative reactive power, it's going to wind up making Q overall smaller. So a better way to perform power factor correction would be using a capacitor while holding the average power constant. So something like this, right? So if this is our correct S new, we can see that P old is unchanged. This is going to be our new reactive power, and theta nu is indeed smaller than it was, okay? So that's how power factor correction works. Essentially, we add capacitance into our system intentionally in order to have the capacitor supply VARs or offset the amount of VARs that the inductance in our system is absorbing, okay? So we could say that, let's say, S old is equal to P old plus JQ old, and S new is equal to P old plus JQ new. Okay. So if I were to take S old minus S new, what I would get is P old plus JQ new minus P old plus JQ old. And the P olds are going to cancel each other out. And what we're going to wind up getting is simply J Q new minus Q old, which is J Q cap. This term Q cap is the reactive power absorbed by the capacitance, and it is always a negative quantity. Okay. So essentially, if we were trying to hit some target power factor, we would need to know how many VARs we need to inject or supply to the system. And then we need to be able to choose a capacitor that is going to provide that specific amount of VARs for us to hit our target. Okay. So what we can do is we can, if I call this guy over here S cap, what I can do is I can set this relationship for complex power that we need to inject into our system equal to this relationship for the complex power that is provided or absorbed by a capacitor. And I can set those guys equal to each other and then use that to solve for what specific capacitor value is going to do what I need for my system. Okay. So if I rearrange those relationships, what I'll wind up getting is the equation C is equal to negative Q cap divided by omega, the angular frequency at which our system is excited, times the magnitude of the voltage drop across the capacitor squared. Now, this equation is correct, but I find it a little difficult to use. And the reason why I find it difficult to use is because usually we know what power factor we're currently operating at. We know what power factor we want to operate at, but there's no clear-cut way for me to apply that information to this equation. So my preferred equation for calculating capacitance is actually this guy, where we're going to have P old. So this is the average power, both before and after power factor correction, because it doesn't change, times the tangent of theta old minus the tangent of theta new divided by omega times the voltage drop across our capacitor squared. So this is the relationship that I put on your equation sheet for exam 3 as well. And now I'm going to show you guys how to use it, okay? So I'm going to work one of your in-class assignment problems with you, and the in-class assignment problems are very representative of the questions that I like to ask you on your exams. And then after that, I'm going to work a web work problem with you that is probably one of the most difficult web work problems that you guys are asked. And if you can follow what we're doing on that web work problem, then you've got power factor correction down for sure. Okay. So let me open up in class assignment number 24 really quickly. So we're going to work this guy right here. We've got a little bit of a word problem, but that's okay. Okay. So we're told that we have a 120 volt RMS system operating at a linear frequency of 60 hertz. Our load is absorbing 4 kilowatts of power at a power factor of 0.8 lagging, and we're trying to find the value of the capacitor to put in parallel with the load in order to raise the power factor to 0.95. So I'm going to draw a little bit of a circuit here. It's not really necessary because this is fairly simple, but I just want you guys to kind of understand what's going on. So we have a voltage source over here. We know that it has a magnitude of 120 volts RMS. Don't know anything about the phase angle, isn't remotely important. It is connected to some load. And what we know about the load, sorry, let me see. Trevor asked, is a power line normally at 60 hertz? So here in the United States, the answer is yes. In Europe, it is 50 hertz. Other nations, practically all nations use 50 or 60 hertz. Japan, for what it's worth, actually uses both. It's a pretty interesting situation. So because they were occupied by both the United States and a European alliance after World War II, the area of the country that was occupied by the US works at 60 hertz frequency. The part of the country that was occupied by the Allied European nations works at 50 hertz. And what separates those two regions is actually a river. So they have frequency conversion stations all along this river so that their whole country is on the same utility grid. Um, the only reason I know that is because I had to design a battery energy storage system for that. And I had to look into what frequency was used where when designing the bus work and figuring out how to power all of the internal equipment for that place. But anyway, so 60 hertz here in the States, 50 hertz in most of Europe and South America and stuff like that. All right, so 4 kilowatts is the power absorbed. And then we're also told that our power factor is 0.8 lagging. And essentially what we're going to do is we're just going to connect a capacitor C in parallel with our voltage source to improve the power factor at which our system is operating. Okay. This is a simplified representation of what's going on, but this is literally what is done in industry. We figure out what value of capacitor, usually it's a bank of capacitors, and then we literally mount it on the pole next to the transformer that is supplying voltage to whatever it is that we're trying to power. Okay. So our equation, just to remind you guys, is C is equal to P old times the tangent of theta old minus the tangent of theta new divided by the magnitude, omega times the magnitude of the voltage drop across the capacitor squared. So I want us to figure out which pieces of information we were already given. So were we given P old?
Yes.
So I agree, but how do we know that we were given P old?
It tells us that the load absorbs 4 kilowatts of power.
Right, and kilowatts is the units of average power, right? So we might have been told that our load absorbs 4 kilovolt amperes, in which case we would have been given apparent power, okay? So we do very much need to pay attention to those units. So kilowatts right here tells us that we're dealing with average power. So we know that P old is 4 kilowatts. Were we given theta old? Well, not exactly, but we can find it pretty easily, right? So PF old is 0.8 lagging. And so from that, theta old is just going to be the inverse cosine of PF old. So when I put that into my calculator, inverse cosine of 0.8. Oh, my calculator is in radians mode. How the hell did that happen? I get 36.8698. So I'm going to call that 870 degrees. Okay. And for what it's worth, I'm storing that in my calculator as X. Okay. Pretty similarly, we weren't given theta nu, but we can find it um, by looking at our target power factor here, right? So if PF nu is equal to 0.95 lagging, then theta nu is just the inverse cosine of PF nu. And so when I do inverse cosine of 0.95, I get 18.19487. So let's call that 0.195 degrees. And I'm storing this in my calculator as y. Now, let me ask you guys a quick question here really quickly. What if our target power factor were 0.95 leading? Would that have any impact on our angle, theta nu?
It should.
It should. So when we talked about leading and lagging power factors on Wednesday, I told you guys that positive angles are indicative of lagging power factors and negative angles are indicative of leading power factors. So if we had a leading power factor, we would actually have to add a negative sign out front here because the inverse cosine operation on your calculator is only going to return an angle between 0 and positive 180 degrees. Okay. So this is a place where we have to remember, leading means negative angles, lagging means positive angles. So anytime we're dealing with a leading power factor, we have to manually add in that negative sign. Okay. So just wanted to make sure that you all were aware of that. All right, so we've got P old taken care of. We've got theta old taken care of. We've got theta new taken care of. How do we find omega?
Then just 60 hertz.
So 60 hertz is our linear frequency. How do we convert that into an angular frequency?
Pi over 180.
Nope, so that's just converting. So 60 hertz times pi over 180 is not going to be an angle. Trevor's right. Or actually, it's not 120 pi. So omega is just 2 pi f, right? Where f is our linear frequency. This is a relationship that we talked about when we had our review of sinusoids. It 100% is on your equation sheet, so you don't have to necessarily remember it, but it's a pretty easy thing to remember. So to go from linear frequency to angular frequency, you just multiply by a factor of 2 pi. So that's just going to be 120 pi radians per second. I feel like the 120 pi is Trevor telling me what omega actually is, not how to convert. Okay, the last thing that we need is the voltage drop across the capacitor, and we only need the magnitude of that. So were we given that information?
Yes.
Yes, it's just 120 volts RMS. So now all we do is just plug that stuff into our equation and it spits out the answer of the size of the capacitor that we need to hit this particular target power factor, right? And I can type it into my calculator if you guys want, but I'm 99.9% sure it's going to just spit out this answer right here, or actually 0.000310439 because I always put everything in my calculator in base units. Okay. So now let's increase the level of difficulty significantly by looking at one of these pesky web work problems. So I'm going to look it up on my second computer here, and I'm just going to write the example out for you guys. So this is homework 24, and I believe it is problem 4. So it's it's the last problem that you're given. Okay. So we are provided with a circuit that looks something like this. Let's see, we're told that this resistor is 5.9 ohms. And then we have a load here. In WebWork, it's just drawn as a small box. I'm going to draw it like a larger box like I did on that last example. And we are told that this load draws 13.8 kilovolt amperes at a power factor of 0.68 lagging. Okay. So we're also given a couple of other pieces of information. So we are told that the magnitude of the current flowing through our load is 24 amps RMS. We're told that our target power factor, or PF new, is 0.94 lagging. And we are also told that our linear excitation frequency is 60 hertz. And once again, we're trying to solve for the capacitor that makes our system operate at a power factor of 0.94 lagging. Okay. So this problem is a bit harder than the baseline problems that I tend to ask, at least on your exams and stuff like that. But I think it's really good practice at making sure that we understand kind of everything that's going on here. So that's why I'm working it with you guys. Okay. So what we need to sort out is, which pieces of information we're given and which pieces of information we were looking for. So I'm going to once again write down our equation for C. So P old tangent theta old, minus tangent theta new. All divided by omega times the magnitude of the voltage drop across the capacitor squared. So I think we were only given essentially theta nu because we were told what PF nu is, and omega because we were told what F is, and everything else we have to solve for, right? So I'm just going to go ahead and write down over here theta nu is just going to be the inverse cosine of PF nu and I get that to be 19.948 and some change degrees. Storing that in my calculator as X. Okay. And omega is once again just 2 pi F. And so that's going to be 120 pi radians per second. All right. So, does anybody have any thoughts on how we're going to solve for any of the other quantities? So, for what it's worth, we still need theta old, P old, and the magnitude of the voltage drop across our capacitor. Okay.
Is theta old just the cosine inverse of 0.68?
So that's a very good question, and it won't be in this particular case. Okay. So 0.68 lagging is the power factor at which our load is operating, but our capacitor is not in parallel with our load. Okay. So our load is in series with that resistor, and that resistor is actually going to tend to improve the power factor at which the voltage source is operating. So realistically, in a problem like this, what we're really trying to use here is the complex power that is supplied by our source. Okay. Because the complex power that is supplied by our source prior to power factor correction is going to be the same as the complex power absorbed by our load, plus the complex power absorbed by our transmission lines that are sending power to the load and all of that kind of good stuff. Okay. So I am suggesting here that the complex power supplied by our voltage source is going to be the complex power absorbed by our 5.9 ohm resistor plus the complex power absorbed by our load. And this complex power right here from our source is going to provide us with, theta old and P old, and we'll also use it to get the magnitude of Vs as well. Okay. So anybody have any thoughts on how I might determine the complex power absorbed by my load? So what information do we know about our load? It's absorbing 13.8 kilovolt amperes, okay? Kilovolt amperes is a unit of what part of the complex power?
The apparent power?
The apparent power, absolutely right, okay? So if we, sorry, I'm going to write this in a different color here. So in our last class meeting, we defined power factor to be average power over apparent power, and it was the same as the cosine of our power factor angle, right? So we already were told our apparent power, so we can literally just put that part in, right? So that's going to be 13.8 kVA. Well, how do we get the angle of our complex power? Well, that's just us figuring out what our power factor angle is. So I think that's going to be the inverse cosine of that 0.68. So if I put this into my calculator, I'm going to put it in as 13.8 times 10 to the 3 angle inverse cosine of 0.68. I wound up getting 93.84 plus J 10,118.327 volt amperes in polar form, or 13.8 with an angle of 47.156 kilovolt amperes in polar form. I feel like I said polar for both, but obviously the first one is in rectangular. Okay. I'm going to store this in my calculator as A for right now. So before I move on from this step, does anybody have any questions about how I used the provided information to calculate the complex power absorbed by our load? So what if instead of being told that we had 13 point, or excuse me, our load was absorbing 13.8 kilovolt amperes, what if it were absorbing 13.8 kilowatts? How would we have found the complex power then? Anybody have any thoughts? All right. Well, in instances where you're given average power instead of apparent power, you can simply rearrange this power factor relationship. And what you'll find is that your average power P is simply, your apparent power is simply P divided by your power factor, okay? So that's one of the things that I see students make the most mistakes on is not recognizing which type of power they were given, which is told to you completely by the units, right? Watts is for average power, volt amperes is for apparent power and complex power, and VARs is for reactive power. So you need to know whether you need to divide by the power factor or not to get your complex power. In this case, because we were provided with apparent power, there was no need for us to do, average power over the power factor because we didn't have an average power to work with. Okay. How might I go about finding the complex power absorbed by our 5.9 ohm resistor?
Can you just use the Ohm's law relationship?
So Ohm's law, we have current, we have resistance. Ohm's law gives us voltage. So that's not quite what I'm looking for.
Would it just be I squared times the resistance?
There we go. Yes. So in the alternative relationships that I gave you guys on Wednesday, and then we also derived a little bit further with them today, whenever we have a resistor, the complex power is nothing more than the current flowing through the resistor, the magnitude of the current flowing through the resistor squared times the resistor value itself. Well, if we look here at our circuit diagram, that current IL is flowing through the resistor and then into the load. So our average power here is just going to be 24 amps RMS squared times 5.9 ohms. Which gives us 3398.4. I'm going to put angle 0 degrees volt amperes, which is the same thing as 3398.4 watts, right? So we know that a resistor of all of the complex power absorbed by a resistor is purely real, so it's the same thing as the average power, okay? So what I'm going to do now is I'm going to add those two complex powers together to get the complex power supplied by my voltage source, right? So what I have stored in my calculator as A plus what I have stored in my calculator as B, sorry, press the wrong button, gives me 12 point, actually, let me write it out this way. 12782.4 plus J 10118.327. This is in volt amperes. And then in polar form, this is going to look like 16302.463 with an angle of 38.365 degrees, volt amperes. Okay. So I told you guys when we started working this problem that this complex power provided by our source, from that I was going to be able to get theta old, P old, and the magnitude of the voltage drop across the voltage source, which is the same as the magnitude of the voltage drop across the capacitor. So let's start with the easy stuff. Which of these numbers is going to be P old?
The 12,000.
Yep. 12,782.4 watts is P old, because the average power is just the real part of the complex power. Okay. Which of these numbers is going to be theta old?
The
38.
38 degrees.
Yep, the 38.365 degrees. Okay. So the only thing that we're missing is the magnitude of the voltage drop. Anybody have any thoughts on how we might find that? So there are a couple of different ways that we can do it, one of which involves making some assumptions. They're not necessarily bad assumptions. I just don't like to make assumptions about anything if I don't have to. Okay. So let's start with the assumption way. Okay. I could, if I were so inclined, assume that the current flowing through my load has an arbitrary phase angle of my choosing. So I might say that this is 24 angle 0 degrees. Okay. Where I'm choosing 0 degrees just to make the math easier. And the reason why I can get away with making this assumption is because ultimately I'm really only interested in figuring out what the magnitude of the voltage drop is. So the phase angle isn't actually important to me. Okay. So that's really the only reason I can make this assumption. But I could use that assumption and back calculate the voltage drop across my load, which would be S load divided by IL conjugate. Okay. Where that voltage drop would be between here and here. And then I can use the information that was provided to me to give me the voltage drop across my resistor. And then I could use Kirchhoff's voltage law around that path to find Vs, under the assumption that we started with a current phase angle of 0, and then I could just take the magnitude of that voltage, okay? That is perfectly okay. And to me, it's actually the more obvious route, but there is a different way that we can do it. But it involves using one of those relationships that I said we don't really have to bother with too much because our calculator does most of it for us. Okay. So that relationship is actually our apparent power equation. And apparent power is nothing more than the magnitude of the current times the magnitude of the voltage. So I am suggesting here that if we take this apparent power and divide it by 24 amps, we will get the voltage drop across our network. Okay. Or at least that's the voltage drop prior to power factor correction, and the voltage shouldn't change when we apply a capacitor across the terminals. Okay. So if we do 16,302.463 volt amperes divided by 24 amps RMS, I wound up getting a voltage of 679.269 volts RMS. And so now I believe we have all of the different parts to plug into our equation here. So we would have, excuse me, C is equal to P old, so that is 12,782.4 watts times the tangent of theta old, which is 38.365 degrees, minus the tangent of theta nu, scrolling up for that guy, 19.948 degrees. All over 120 pi times 679.269 volts RMS squared. Give me just a moment to save a couple of things in my calculator. So I just save that as Z. I just saved that as T. And let me double check. Yep, I saved that as Y. So I'm going to have Z multiplied by tangent of X minus tangent Y all over 120 pi times T squared. Actually, That should be tangent y minus tangent x. I think that's just going to change the sign, but I want to make sure. I got a negative number. Yep, that would have just changed the sign. And I wind up getting 3.1498 times 10 to the minus 5 farads, which is the same thing as 31.498 microfarads. And now, just to make sure for sanity's purposes, I'm going to throw that into WebWork and make sure that it gives me the right answer. Yep. Yeah, so I got the good WebWork green telling me that I haven't made any mistakes there. Okay. So for what it's worth, that is literally the hardest power factor correction problem that you will be asked in Circuits 1. So if you could follow the analysis and the reasoning there, you are good to go on this material. For all of the stuff that you should expect to see related to this on your exam, it is going to be incredibly similar to the ICA problems. And if you look at the old practice tests, you will see it is usually a much, much less involved problem than this. Okay. All right. That's really all that I wanted to talk about for today. So you are more than welcome to start working on problem 2 for the in-class assignment. Or if you have any questions about any of the old exams or anything like that, I would be happy to answer those. If not, I have enjoyed talking into the void to you guys this summer. And I guess I'll see you in the fall.